Greetings, students. This is the third set of notes in the Astronomy unit, Astronomy Part 3, the Earth. On this recording, you should be writing down everything you see in orange text, including what you see right now. This is the title of the notes. So write it down at the top of the page, or type it if you're typing these, and make it a little bit bigger than the rest of the text. So here's a picture of the Earth from outer space. It's interesting to note that pictures like this didn't always exist. It wasn't until people started sending satellites and space shuttles and space stations up into orbit that we could get a picture like this. And pictures like this from the 1960s and 70s were credited with kind of starting the environmental movement, because when you see our actual planet hanging in the emptiness of outer space, you kind of realize how small we are, and how the planet that we have is the only one we have. Earth is our home planet. It's the only planet in the solar system, galaxy, or universe that's known to contain large amounts of liquid water. It's the only planet in the solar system, galaxy, or universe known to contain water naturally occurring in all three phases, and it's the only planet known to have life. So for this slide, you write down, Earth is the only planet known to contain large amounts of water and life. Here is a picture of a location on our planet that shows water in all three phases. There are small amounts of water on other planets, but usually only in one phase. So here you've got ice, liquid, and gaseous water in the clouds. Earth's orbit around the sun is not a perfect circle. It's slightly elliptical. That's a fancy way of saying oval-shaped. On average, Earth's distance from the sun is 150 million kilometers. Earth's distance from the sun is just perfect for life. If we were a little further away, temperatures would be too cold. If we were a little closer, temperatures would be too hot. This perfect distance is called the habitable zone, sometimes referred to as the Goldilocks zone. Not too hot, not too cold. Earth's axis is tilted. The axial tilt is about 23.5 degrees. This affects the amount of solar energy, also known as incident solar radiation, that reaches the surface in a given location. If you're near the equator, you're getting more direct solar radiation. If you're near the poles, you're only getting sunlight at an angle, and you're certainly getting less of that sunlight as well. And here's a diagram illustrating that point. Sun's rays are not as intense when they're hitting the surface at an angle. So for half of the year, the northern hemisphere is pointed at the sun, and the southern hemisphere is pointed away from the sun. And then for the other half of the year, the hemispheres are flipped, with the southern hemisphere pointed at the sun and the northern hemisphere pointed away. This is what causes the seasons. When it's winter in the northern hemisphere, it's summer in the south, and the opposite is also true. So the seasons are caused by the tilt of the Earth. Here's a diagram showing the seasons. On December 22nd, which is the winter solstice, the shortest day of the year in the northern hemisphere, our hemisphere, the northern hemisphere, is tilted away from the sun. So we spend more of our day, of our 24-hour day, on the dark side of the planet. On June 22nd, 6 months later, it's our summer solstice, which is the longest day of the year. And we are tilted towards the sun, and we spend more of our 24-hour day in that illuminated half of the planet. The planet's always half sunlight and half dark. But if you're tilted towards the sun, as we are in our summer, June, July, August, then you spend more of a 24-hour day illuminated. And from our perspective on the surface, the sun's pathway changes as well. During the summer, the sun takes a longer path across the sky, and during the winter, it takes a shorter path across the sky. And it doesn't go as high on the sky. It stays closer to the horizon in the winter. This is an ancient megalithic site in England known as Stonehenge that ancient peoples built in order to frame the sun perfectly on, I believe it's the summer solstice. The solstices were very important to ancient cultures because it helped with them figuring out agriculture. Because it was important when you planted your crops and when you harvested your crops. And to keep track of time, they kept track of the sun and the stars to some extent. So here's a chart showing the different solstices in the northern hemisphere as well as the spring and autumn equinox. So the summer solstice is the longest day of the year. For us, that's June 22nd. The winter solstice is the shortest day of the year. For us, that's December 22nd. And it's flipped in the southern hemisphere. If you're in Australia, it's hot in December, and you have longer days in December. The equinox is when we have day and night for exactly 12 hours. There's a spring equinox on March 21st and an autumn equinox on September 21st. And this is how we mark the seasons. This picture is called Earthrise. It's taken from the surface of the moon, which is pretty wild. But if you're standing on the surface of the moon, your whole perspective changes and the Earth appears to orbit you. So the Earth-Moon system. Earth has one natural satellite, the Moon. It is 384,000 kilometers away from Earth. The Moon orbits the Earth every 27.3 days. And the Moon goes through phases from our perspective. Just like the Earth, the Moon is always half illuminated by the sun. But because we're on Earth and the Moon is orbiting us, sometimes we see the full illuminated side, and sometimes we see only the dark side, and lots of times we see part of both. You're going to have to know this by memory, and I'm going to ask you to draw this repeatedly. But starting with the new moon, it goes to waxing crescent, and then to first quarter, and then to waxing gibbous, and then to full. And from full moon, it goes to waning gibbous, then to third quarter, and then to waning crescent, and back to new. At a new moon, we're just looking at the dark side of the moon. And at a full moon, we're just looking at the illuminated side of the moon. It's important to remember that the direction is always the same. It's always light from the right. So starting at the new moon, the first thing is the waxing crescent. That's a little bit of light on the right side. So 50% of the moon is always illuminated by the sun. Sometimes we see the light side, sometimes we see the dark side, or part of both. This is called the cycle of moon phases. A full cycle is called the lunar month, and it takes 29.5 days to complete. And you can draw it like this as well, starting with the new moon, dark, and then light from the right, waxing crescent, then first quarter, waxing gibbous, then full, then waning gibbous, last quarter, and waning crescent. The moon is believed to have formed when Earth collided with another planet 4.5 billion years ago. So early in Earth's history, it's believed that Earth collided with another planet, and the moon was broken off. The moon itself is densely cratered from impacts of asteroids. So in the early history of the solar system, there were a lot more impacts taking place than there are now. The orbital period and period of the moon's rotation are equal. The time it takes to orbit the Earth is the exact same time it takes to spin on its axis, so the same side of the moon is always facing us during a full moon. Eclipses. Solar eclipses occur when the moon blocks sunlight from the Earth's surface. And there's also something called a lunar eclipse when the Earth blocks sunlight from reaching the moon's surface. So here's a diagram of a solar eclipse. It can only happen during the new moon phase, when we see the darker side of the moon. There are two parts of the shadow that the moon casts on the Earth. There's the umbra, which is the dark part, and the penumbra, which is slightly lighter. If you're inside the umbra, you see the full solar eclipse. The moon completely covers the sun, except for the corona. And the penumbra, if you're in that, you see a partial eclipse. There was a partial eclipse a couple years back here in Virginia. We were in the penumbra of the shadow at that time. The outer edge of the sun is called the corona. That's what's visible during the eclipse. Never look at the sun during the eclipse, unless you have special glasses. So why isn't there a solar eclipse every single time there's a new moon? It's because the moon's orbit is tilted. Most of the time, shadows don't line up. So it's either slightly above or slightly below, casting a shadow not on the Earth. There are, in fact, an average of 4 solar eclipses every year, but if you're not in the right place at the right time, you'll miss it. Most of the time, they fall over the ocean. A lunar eclipse is when the Earth casts a shadow on the moon. Since the Earth is bigger than the moon, it casts a larger umbra, but there's also a penumbra in this case. And a lunar eclipse can only happen during a full moon, because the sun, the Earth, and the moon are all lined up. And if the Earth is going to have to cast a shadow on the moon, it has to be between the sun and the moon. Here's a picture of a lunar eclipse in progress. We checked out this picture in class during a snapshot if you were there that day. This is a picture of a location where there's a very extreme variation in tides. The bottom picture is a high tide, the top picture is a low tide. The tides are the periodic rise and fall of water level caused by the gravitational pull of the sun and moon. There are 2 high tides and 2 low tides each day everywhere on Earth. The moon has a greater effect on the tides than the sun because it is closer to us. The strongest tides happen during the new and full moon when the sun, Earth, and moon are all lined up. So at the top there you have the new moon and full moon positions. That's called a spring tide, and it's a stronger tide. When it's a first quarter or third quarter moon and the sun, moon, and Earth form a 90-degree angle, it is a weaker tide. It's called a neap tide. Spring tides occur during the full and new moon phases when the sun, Earth, and moon are lined up. During the spring tide, high tide is higher and low tide is lower. This diagram represents a neap tide. Neap tide happens during the first and last quarter moon phases when the moon, sun, and Earth are at a 90-degree angle. In a neap tide, high tide is not as high. So here is a final slide with all of the words that I asked you to write down. Your slide in your digital notebook can look like this, but you should type it up yourself. If you screenshot it, you're not going to get full credit. And some students prefer to handwrite it. If you handwrite it, you have to snap a photograph of it and put it in your digital notebook. But if you need to, you can pause the video here and catch up on anything that you missed. And I will see you later.